So I wrote here, lesson 7, parallel plate force problems. Recall from our last lesson, so we said if you have parallel plates, metal plates, and you charge one positive and one negative, or more often, Colin, you just hook one end up to the ground, the electric field is given by that. Now, that also means that the force between those plates on a charge stuck between those plates is given by that. Except since electric field, you know what? It means that the force is given by Q times the voltage divided by the distance between the plates. Yet another equation. All I did was I substituted this in for electric field between plates. Colin, you asked about direction. It's away from the positive towards the negative, or if they're both positive, towards the less positive. That's the direction of the electric field. So now we can start to talk about a phenomenon called ionization. What's an ion? You learn in science, an ion is a charged particle, a charged element. Really what we say is an ion is when an electron has been forcibly removed. So I wrote here, explain why an atom will be ionized, the electron will be separated from the atom, if it's placed in a sufficiently large electric field. So here's an electron. What are the forces acting on it? Well, it's attracted to the positive nucleus, and that's what's holding it in the atom. However, because force equals Q, if E is large, that external electric field, it will be bigger than, this force will be bigger than the K, Q1, Q2 over R squared between the positive nucleus and the electron. And if I can make, and the electric field, Colin, I can bump that up. Especially if it's between plates, it's going to be, I just bump up the voltage. And that we can do with all circuits. You okay with that? Yeah? Okay. So it's possible to rip an electron off of an atom. You've now ionized the atom, and you've got a free electron. Sorry, I should be careful. An electric field pointing to the right will make an electron actually rip off to the left, won't it? Because it's which way would a positive want to move if it could. The electron will travel that way. Right? Okay. If we're talking about air, the atmosphere, which is mostly nitrogen, N2, and oxygen, O2, and other trace gases, it takes about 3 million volts per meter. This is the electric field that you need to ionize air, to rip electrons off of air molecules and start passing them from one to another, to get a spark. This may seem like a lot, but in actual fact, ionization of the air occurs actually quite frequently. It's the crackle we hear when we pull apart clothes that come out of the clothes dryer. It's the shock we get when we walk across a carpet on a cold winter day and then reach for a doorknob and it's lightning. So let me give you good old John Travoltage. Here he is. Come on, John. You can load. In theory. Gonna work. People at YouTube are going, boy, this is thrilling content. Here we go. Good old John. Okay? So John, when he rubs his foot on the carpet, he's rubbing electrons off onto him. Now, they're going to try and gather on the outside of him because they repel each other. That's, by the way, explains that really strange tingly feeling you get on a dry winter day. You've gathered enough electrons that actually the hair on your skin is standing straight up because the electrons have gathered on the end of it and they're repelling each other. And that's, you're not used to that feeling. What's weird on a dry, really a cold, dry, wintry day works great for that. Now, eventually, eventually, if he builds up enough of a charge, then the air will ionize and he'll get a shock. Okay? Now, if he lowers the distance, he doesn't have to build as big a charge. That's why the spark won't jump. The spark won't jump. When exactly you get enough distance that the air can ionize and jump the gap, that's when you'll get a shock. But you'll notice if you watch closely, if you touch a doorknob, you always get the shock before you touch it, not when you touch it. It always jumps just before you get there. Good old John. Each of these effects is accompanied by light. The light occurs because that ionized electron does not remain free. It's got higher energy. It wants to fall into the shell of a neighboring atom. And to do that, some of its energy has to go away. Law of conservation of energy. It gives off a photon of light. Light is a form of energy. Let's really talk more about, shocks are great. Lightning. You can imagine that a cloud is roughly like a parallel plate. The flat bottom of a thunderhead, it's reasonably flat. It acts kind of like a parallel plate. And the Earth is flat. Now, I know they're curved. The Earth is curved, and the thunderhead has bumps. This is a rough simulation, but it's pretty good. It's pretty good. So suppose the bottom of a cloud is charged to 2.5 times 10 to the 8th volts by cosmic rays that pass through the atmosphere. How close does the ground need to be for a lightning bolt to occur? Keep in mind that the air breaks down at about 3 million volts per meter. Volts per what? Volts per what? You know what? This is the electric field. In this case, the electric field is 3 million volts per meter. We know that the voltage that this cloud has is 2.5 times 10 to the 8th. And we would like to figure out how far the cloud needs to be away, how close the cloud needs to be to the ground for the spark to occur, for lightning to occur. Can you see, this is our equation from yesterday. Yesterday we said you can find the electric field between plates if you know the voltage divided by the distance. Here, Jake, we want to get the voltage, so we want to get the distance by itself. How would I get the distance by itself, folks? Hey, is this one fraction equals one fraction? Well, you know what? Stuff moves diagonally. The D can move to there, the E can move to there. The electric field can move to there. Distance is going to be the voltage divided by the electric field. It's going to be 2.5 times 10 to the 8th divided by, instead of writing 3 million, can I go 3 times 10 to the 6th because that's less typing? How close does this cloud need to be to the ground for lightning to occur? Yep. Okay. What if the cloud has a bigger voltage? Then the cloud doesn't have to be as close to the Earth. Lightning can jump further. Smaller, because by the way, this isn't changing. This is just a result. It turns out the ionization factor of the air, the electric field required to ionize the air, is right around 3 million. That's pretty constant. It does vary based on humidity and temperature and a few other things, but 3 million is a nice number to use. Okay. So, where would you not want to be in a lightning storm? You would not want to be around anything that lowers that distance. Let's suppose that that cloud is 90 meters off the ground. Can lightning reach the ground? No. Could lightning reach the top of the tree because it's higher than, that might be enough. So you would not want to be here or here because you've physically closed that distance yourself on the mountain. Okay. If the boat was a sailboat with a metal mast, which essentially is a lightning rod, you probably wouldn't want to be on it. Out east, I'm hoping to buy a sailboat someday, so I'm reading a bit about sailing. Here on the West Coast, we don't get the lightning storms the same way they do in the southern Atlantic. But boy, you read stories of people that sail in the Florida area, and you're always watching for thunderheads on the horizon. And if you see a thunderhead on the horizon, you get out of there as fast as you can, no matter what kind of a day you had planned. You bail, because you're basically sitting in a lightning rod. Lightning, if it was close enough to strike the water, you also don't want to be on the water, even in a regular boat, just because the water can conduct the electricity quite well.
Doesn't lightning strike the tallest thing in the area?
Why?
Because it's closest.
Why? Yeah. What's really happening, by the way, is the voltage is building, the voltage is building, the voltage is building, the voltage is building. As soon as there is something close enough, the tallest object, then you'll have the discharge, and the voltage will go back down to zero again. Yeah. And so that's also the idea behind the lightning rods, which are deliberately built into buildings, and then there's big wires attached to them to funnel all that extra charge to the ground without damaging the building per se. Yeah. Put your pencils down, look up. So, recall that if we know the electric field, we can find the force by going QE, which really also is a nice shortcut as opposed to having to go K, Q1, Q2 over R squared. And will we know the electric field? Colin, between parallel plates, the electric field is just the voltage divided by the distance, which is pretty quick to calculate as well. This is my rant from last day about saying, you know what, parallel plates give us some much nicer mathematics, just less typing in our calculators. So example 4, I like example 4, I like example 4. Tice, what's example 4 asking me to find? A equals question mark? Well, the two main ways to find acceleration are good old physics 11, VF equals VI plus 8, D equals VIT plus VF squared, or forces. I'm leaning towards forces given that we've been looking at what's the word forces. So I'm going to try going like this. F equals MA. By the way, normally I would say, what are the forces acting on this electron? And I would say get the obvious one, but what's the mass of an electron? So close to 0 that the obvious one on an electron is negligible. We're going to ignore mg. Not even worth it. Not even worth it. Okay? Which way is this electron going to want to move, by the way? Up or down? Up. Which way is the electric field, up or down? Down. Down. Okay? Which force? Well, it's an electric force, and I can find an electric force by going QE. The electric field. Did they tell me the electric field between these plates? No. Wait a minute. I can find the electric field between these plates by using Q, the voltage, divided by the distance equals MA. I've stopped writing vectors now because which way did you guys say this electron is going to accelerate? Up. I got the direction. Speaking of accelerate, Jordan, how would I get the M by itself? So how would I get the A by itself? Whoops. So the acceleration here is going to be the charge times the voltage divided by the mass and the distance. What's the charge? I would say it's an electron. And I don't think I'm going to put the negative in here. Acceleration is a vector, and I figured out the direction anyways. So 1.6 times 10 to the negative 19. What's the voltage that it's traveling through? 275 volts. Mass of an electron. I know it's 9.11, but I can't remember the 10 to the. I know it's negative as well. 10 to the negative. D, please don't say 2.5. 0.025. Okay. Crunch the numbers. It's going to be big. Do you get that? Wait a minute, Mr. Dewick, Devin says. That's 1.9 times 10 to the 15th, yeah? But the speed of light is 3 times 10 to the 8th. Mr. Dewick, aren't you telling me that this electron is going faster than light? No. It would be going faster than light if I allowed it to accelerate for an entire second. How far is it traveling? You can actually let VI be 0, and you can actually calculate VF, and you'll find it doesn't violate relativity. It's not, based on this, it's not going to make it faster than the speed of light. It won't get that fast. So it's got a crazy huge acceleration, but that distance traveled is going to be traveling for such a tiny time, although it's going to be speeding up, it's not violating the laws of the universe. 1.93 times 10 to the 1.93.
The bigger the distance, the smaller the
Ah. See, the universe takes care of its own. We're good. Yeah. As distance goes up, acceleration goes down. Okay. Wait a minute, Mr. Dewick. What if you bumped the voltage up? Then what would happen? Okay. By the way, and this is really, all the Large Hadron Collider is the mother of all voltages. I don't know how big the voltage is in that thing, but it's pretty impressive. I think they're using enough voltage, the equivalent of a medium-sized town.
How do they get it?
How do they get the voltage?
Yeah.
Patience. Towards the end of in fact, the last lesson of the year. Sorry. It's using something called a transformer, not the cartoon or the movies. It turns out it's a very clever, easy electric device where you can step up or step down a voltage. The higher your voltage, the lower your current's going to be. Trying to remember, do they have access to a nuclear reactor? Because I know France has nuclear reactors, and they're on the border of France and Switzerland, and Europe, they do have some nuclear reactors. They're not as terrified of it as we are in North America. Editorializing for a second, as we foolishly are in North America, but I'll leave that alone. So, this is how we calculated the charge on an electron in a very famous experiment. A scientist named Millikan used parallel metal plates to hold in place a charged oil drop. It remained in place because the electric force up equaled the gravity force down. So, here's an example. Example 5. The charged oil drop below is at rest due to balanced gravity and electrical forces. The first question is, what is the sign of the charge on the oil drop? Well, what are the forces acting on this? We have gravity down. We have electric force up, Fe, same size. So if the electric force is up, which way does this charge want to move? Up. So is it negative or is it positive if it wants to move up? It's negative. Which way is the electric field? Down. Okay, so the first thing I would say is negative. B says, write a force equation. You know what? I would normally go winner minus loser, but Jordan, this one is in balance. I can actually just say the electric force equals mg. I can even take it further. Q times the electric field equals mg. I can even take it further. Q times the voltage divided by the distance between the plates equals mg. And then what Millikan did to find the charge on an electron is he got the Q by itself. And he knew with some accuracy how many, using Avogadro's number, how many molecules there were in this charged droplet, and therefore how many electrons there were in this charged droplet, and therefore what the charge on each electron must be. It's a simplified version. I have a video I might show you later if I have time. So, Example 6, a particle of mass blah 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 and charge -3 electrons is held suspended between parallel plates. What's the voltage on the upper plate in order to keep the charge in equilibrium? If it's held suspended, we're saying that. In fact, Cade, it seems to me we can just take this final equation that we ended up deriving. Q, change in voltage, over D equals mg. Cade, what's this question want me to find? Oh, how would I get the V by itself? Yeah, multiply the D and divide by the? Okay. Which Q? I guess 3 electrons. Oh, by the way, that upper voltage, is it going to be negative or positive? I think if it's holding up some negative charges, if it's attracting some negative charges, I think the upper voltage is going to be positive. So I know the answer is positive. I'm not going to worry about putting plus or minus signs in or vectors or anything like that. So Cade, you said the voltage is going to be mgd over Q? I agree. M, this time they told me the mass, 2.3 times 10 to the negative 14. Yay! G, 9.8. D, 0.015. Q, 3 electrons. 3 times 1.6 times 10 to the negative 19. How many volts would we want to have in this system? How many volts would we hook this up to? And voltages, Colin, we can, with circuitry, control with pinpoint accuracy. Even with old analog, fairly basic circuitry long before we went all computerized and digital, we can control that pretty well. You get 7,040 volts? Yep. That'd do it. Okay. So just giving you ways that we can use forces between plates. Homework. How many volts were on your hand if you get a shock when your finger is 0.05 millimeters away, remembering that air breaks down in an electric field of about 300 million volts per meter? 2 works. 3 works. 4 is good. 5 is good. What does number 5 want you to find? I would use the change in potential plus the change in kinetic, although I think the change in kinetic is 0. And for potential energy, I would use Colin's shortcut of QB. Way nicer. Way nicer. That's going to be the next lesson, but there's a little preview of coming attractions. Colin, what's number 6 asking me to find? You might be able to do that using energy, or you could find the force, find the acceleration, and find V final, like we did. We talked about with that one that wasn't going to pass the speed of light. 8 is good. I skipped 7. 9 is good. 10 is good. We already did 11. Okay. Finish the take-home quiz. And now I got a couple of more videos to show.